Then we have the behavior of capacitors, multiple capacitors as groups. Okay. So if I take three capacitors, C1, C2, and C3, and connect them in series, the interesting thing, and again, you don't need to memorize it. The one thing that you do need to recognize is that its behavior is opposite of a resistor. Why? Because the effective capacitance, if I want to replace all of these capacitors, three capacitors, with just C series, okay, and I need to find an ohmic value for this guy, how will I, I need to find value of the unit of capacitor is farads. If I want to replace it with one capacitor with a particular farads, then what will that value be? It will not be C1 plus C2 plus C3, the farads for capacitor 1 plus the farads for capacitor 2 plus the farads for capacitor 3. No, that's not how the capacitors add in series, the capacitances, okay? They add just like the reciprocal parallel formula for the resistors, okay? The effective capacitance of a capacitor in series, okay, of multiple capacitors in series, using this formula is going to be less than the smallest capacitor. And try it out. Okay, let's say this is 1 farad. Let's say this is 2 farad. Let's say this is 3 farad. I can guarantee you that C series is going to be less than 1 farad, right? Because that's how the reciprocal formula works. So if you want to try it out, it's going to be 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3, right? So what do we get? It is going to be equal to 1 divided by 1 plus 0.5 plus 0.3. So this is 1 divided by 1.83. And you can already see that this number is going to be less than 1. Does it make sense? Okay, that's how the capacitors act in series, their effective capacitance. When we look at them in parallel, they're opposite. They simply add their farads, their capacitances together with simple summation to give you the equivalent capacitance. Okay, and this is a behavior of resistors in series. So in summary, and what happens in with the series formula, the C equivalent is going to be larger than the largest. Okay, again, let's use this example. Let's say we have 1 farad, we have 2 farad, and we have 3 farad. I guarantee you that C total for parallel is going to be larger than the largest, which is 3F, right? Pretty simple, because 1 plus 2 plus 3 is definitely greater than 3. Make sense? Okay, so this is something that we need to be very careful about, because the general tendency I notice among students when they're preparing for FE electrical PE power, doing these type of problems, is just to add everything in series as a simple summation. And as soon as the word parallel shows up, or you see a configuration that is parallel, they'll just use the reciprocal sum formula. Wrong. Okay, easy points to lose. But I would like to remind you that so far we are talking about capacitance. Okay, there are two other things that we need to understand about capacitors. They are its reactance, capacitive reactance, identified typically with X of C. And the other thing is the impedance of a capacitor. Now, and the first thing that we've basically been spending time on is the capacitance. So capacitance is a material property. It depends on the dimensions of the material, right? The wafer or the plates or whatever you have, the dielectric strength, right? The voltage and so on. But the fact of the matter is that it is so far independent of the frequency. The frequency is now going to come into play. It's a very important component. So we introduce a new concept, which is called the capacitive reactance. And it shows that the capacitance of a capacitor is actually influenced, right? Or more specifically, the impedance is influenced by the frequency. So X of C is equal to 1 divided by omega C. Now, there are a couple of different ways. Sometimes you actually include a negative sign over here. That's how the reference handbook shows it. Some textbooks omit the reference, the negative sign, and they basically just simply show that Z of C is equal to 1 divided by J omega C. And if you guys are interested in knowing where the negative sign comes from, we actually multiply and divide it by J. So you end up with J divided by omega C, and you have a denominator of J square, and J square is equal to -1. Okay, that's where the negative sign comes from. And then they basically say that, okay, this can be expressed as -1 divided by omega C multiplied by J. So this term, which is this guy over here, -1 over omega C, basically is equal to XC. It's neither here nor there as long as you understand the fundamentals. The key concept that I want to explain you very quickly over here is that this X of C is a function of omega, this Z of C is a function of omega. Okay. Now, how does omega, and omega, for those of you who want a quick refresher, omega is simply equal to 2 pi f, and f is your frequency in hertz. Okay. Now, the question is, how does this omega impact the reactance, and more importantly, the impedance? Okay. As you can see that the omega is residing in the denominator, right? So if we crank up the value of omega, all right, guys, then what happens to X of C? What happens to the impedance? It is going to reduce, right? Makes sense? Because it's inversely related, right? So the higher the frequency, the lower the impedance, the lower the reactance of a capacitor, okay? And the lower the frequency, the higher the impedance, higher the reactance. Now, let me ask you this. Let's say that I put a box around it, a box around it, a box around this guy. I call this one as ZC1. I call this one as ZC2. I call this one as ZC3. Impedance of capacitor C1, impedance of capacitor C2, impedance of capacitor C3. And I ask you to figure out Z total for me. And this is the question. Are you going to use the reciprocal formula, or you are going to use the series, simple series formula when I ask you about this? Feel free to send me a message via by selecting everyone, by selecting host and panelists, whatever you feel like, publicly or privately. What do you guys think? Series? A lot of you guys are saying series. Parallel? You are selecting parallel. The correct answer is that impedance always, always, always adds up in series, regardless of whether you have a resistor here, regardless of whether you have an inductor here, regardless of whether you have a capacitor here. If you have a cap, this is simply going to be 1 divided by j omega c. If you have a resistor, this is simply going to be R. If you have an inductor, this is simply going to be j omega L. It doesn't care what is inside the box. This is going to be the sum of ZC1 plus ZC2 plus ZC3. And this already answers the second question, that if I have, this is a series, okay? If I have parallel, right? Then what will be the arrangement? 1 divided by 1 by Z1 plus 1 divided by Z2, Z3, and so on. If you have parallel arrangement, and if we call them boxes of impedance, we don't care what is inside those boxes, as long as obviously we handle those formulas properly. We just use a reciprocal formula. Important concept. What I see students mixing and confusing all the time are the formulas for capacitance in series and parallel with the formulas for the impedance in series and parallel. Okay. And the lack in understanding stems from the fact that they don't appreciate the difference between capacitance, reactance, and impedance. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for every electrical and P power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and P-Power exam preparation programs, please visit my website, studyforfe.com.